So we have learned or reviewed some basic statistical descriptions of data using mean, deviation, 5-number summaries. This is the time we need to also review our concept of hypothesis testing. Although this class will not actually use hypothesis testing directly that often, but the idea of probability distribution is a key, a foundational concept. So we need to review that. Hypothesis testing is a scientific process of testing whether or not a hypothesis is plausible. In the example of means, we have collected data and we obtained a sample mean from the data that we collected, but do we know if that mean actually represents the population mean, right? So there are many hypothesis testing, but all of the hypothesis testing has a test statistic, and this test statistic follows a certain distribution. So the example of testing a sample mean against the population mean, this can be done using the Z statistic. This Z score follows a normal distribution. I want to note that this graph is not very accurately plotted. The end of the curve will never reach the horizontal line. It's approaching the line constantly, but never really meets it. So there's always tiny probabilities for those rare events to happen. That's a side note. So z-score follows a normal distribution. This is a standard normal distribution curve. Let's review some of the key concepts. The central line is 0. That's the mean. A standard normal distribution have the mean at 0 and the standard deviation is 1. Okay, so various z-score might fall at different places on the horizontal line, and that indicates the probability for that value to happen. And the areas under a z-score, if you draw a vertical line up and meet the curve, and this creates an area, and this is the area that tells you the probability for we observe another z-score that's smaller than this current z-score. Okay, so this is our z distribution, which is normal. Okay, then we can use this to do this hypothesis testing. There's two ways we can do it. We can to test whether our sample mean is the same as the population mean. We can have either a two-tailed test or a one-tailed test. When we do a hypothesis testing, we always have to specify a significance level. This significance level indicates how much risk we want to take when that non-hypothesis is true. It's really true, but we found it's false. So this 1 minus significance level is our confidence level. So how much confidence we would want to believe in our test result. So a significance level at 5% means that we have a confidence level of 95%. Okay, so non-hypothesis is in a two-tailed test, we care whether our sample mean is really the population mean. What if either the sample mean is not, whether it's greater or smaller, they are going to prove that alternative hypothesis, which is our sample mean is not the population mean will be true, will be found to be true. Okay. So again, this is our normal distribution, the Z curve. Recall from our earlier discussion, 95% of the data are going to occur within two standard deviation. So 1.96 standard deviation between the negative side and the positive side. This covers the 95% of the data. Therefore, when we have our significance level at 5%, then this represents 2.5%. This represents another 2.5%. If our z-score, after computing our sample mean against the population mean, against the population deviation, standard deviation, and the sample size, if we found our z-score fall in those little areas, either of those areas, then we would reject our null hypothesis. Because if our sample mean is really represents the population mean, then it should be closer to the mean of the z-score. It should closer to the central line. The further away our z-score is, indicates that our sample mean is further away from the population mean, right? So when they go out to our confidence areas, we entered rejection area. So this is our rejection area. So if we compute, given our sample number, sample mean, and those numbers, if we found a z-score falling into those areas, we would reject our null hypothesis and accept the alternative hypothesis. Okay. Such test could also be run as a one-tailed test. If you have this test will only tell us whether our sample mean is the same or not the same as a population mean. If you want to test whether the sample mean is greater than or less than the population mean, you will use a one-tailed test. So for a z-test for a one-tailed test can be depicted in this graph. So here, our null hypothesis is sample mean is smaller than population mean. Our alternative hypothesis then is the opposite of the null hypothesis, right? So the opposite is the sample mean is actually greater than the population mean. In this case, we only care about the positive side. Our rejection area is going to be in the positive side because our null hypothesis is our sample is smaller. So if our sample is smaller, it should fall in this area. If the z-score actually falls into this area, that's a strong indication that our sample mean is greater than the population mean, not smaller. Therefore, for a one-tailed test, our rejection area will be here. And this area totally represents 5%, right? Because we're not splitting them, we're putting them together. So our confidence level, our confidence area is this. Our rejection area is this 5% area. And this would be our critical value. So this here is 1.645. If we are 1.645 greater than this critical value, then we fall into the rejection area. Okay. So run a real example I took from a tutorial. So in this example, we have IQ scores. We sampled 30 students and found the average IQ score is 112. And we know the population's IQ score is 100. And the population standard deviation is 15. Using our Z statistics formula, we can find this Z score that we have is 4.6 Our alternative hypothesis is our mean is greater than 100, is better than general population. Therefore, we are performing a one-tailed test. So one-tailed test is this graph, right? So we're looking at the critical value of 1.645. This is 1.465, and this is a 5% area. Our score it has found to be further from, it's greater than 1.645, therefore it has to be here, because here is 1.645, right? Then we can see that our score falls into the rejection area, therefore we reject the null hypothesis and accept our alternative hypothesis that this our sample mean, our students' intelligence is better than the general population's IQ. Okay, so the idea is really we need to get to understand a distribution curve, how to read a curve, what is the area means under it, what's the critical area. Those are the fundamental concepts that we need to obtain. Other tests, so I listed other tests for means, and there are a lot of more tests, as we know that this class is not a statistical class, therefore we won't cover any of those. However, I want to mention that in one difference in data mining application of statistics is that we want to use the power of statistical methods to give indications and to guide us in our data mining tasks, but we don't actually check all those assumptions. For any parametric statistical test, there are always a set of assumptions that you need. When you do statistical analysis, you must check them and make sure you meet those assumptions before you actually run the test. For example, the one sample z-test we just performed, it requires data to be normally distributed, and you have a known population deviation, and your sample size need to be greater than 30. If you don't meet all those criteria, you should not use this z-test. T-test and all the other tests all have those assumptions. You need to check every one of them before you use them. But in data mining tasks, we don't actually perform those checks. We run those tests and see what insight we could get. Those are not really accurate indications, but they give us intuition, some directions. So later, I think maybe next week, we will start to see how we actually use chi-square test, and we don't check the variation. We don't check the assumption, sorry. But we develop algorithms based on chi-square test ideas. It works. So that's it. Once it works, then we are happy. Okay, I think I'm going to conclude this video and start another video.